Hello class, and welcome to today's algebra lesson, which is about the transformation of linear functions. By the end of today's lesson, you will be able to apply translations, dilations, and reflections to linear functions. So first, what we need to understand is where our base is. What are we starting by looking at? We are starting by looking at the parent function, which is the simplest form of a function in any family. The family is the different types of graphs. So in our case, we are looking at lines. There's a graph that looks like a U, that would be a different family. There's one that looks more like an S, that would be a different family. For our purpose, the family of functions is straight lines. The most simple function is y equals x. Everything else that's built up around a line is based on y equals x. And we get into that slope-intercept form of y equals mx plus b. The slope and the intercepts being everything that we can change about the function. This function has a slope of 1 and a y-intercept of 0. That's why it's our most basic function. It's the simplest slope with the simplest y-intercept. Our transformations are how we move it around the graph. So it's every slope that's not 1 with every intercept that's not 0. There are 3 different types of transformations that we have. The first one is a translation. That's where the line is just being slid around the graph. The angle of the line stays the same. The dilations are moving it around the graph and also changing the angle. The reflections is where we are flipping the line over on itself. For our purposes, we're going to be flipping the line across the y-axis. So we're going to start by looking at the translations. Again, this is where we slide the line around the graph. This is going to keep the slope the same. It's not going to change the tilt of the line. It's only going to change the y-intercept. When we translate, we can move up and down, the vertical, or the right and left, horizontal. So I'm going to start with a function of f of x is equal to x plus 4. F of x is always going to be your starting function that you're looking at. Anything other than f, so in this case I use g of x for my examples, are going to tell you that something has changed. So with our vertical translations, we're adding a number onto the end. So in this case, I said g of x is equal to 4, or x plus 4 plus 3, which actually simplifies to x plus 7. So what that did was move the function up. So if I look here, if I add 3, 1, 2, 3, it moves my function up. If I have the other vertical translation, which in this case I chose subtracting 3, that would give us a final equation of y equals x plus 1. That moved the function down. So when I moved it down, 1, 2, 3, I ended up with a y-intercept of 1 and still my slope of 1. So I moved that function down 3 spaces. So if you are adding a number at the end and your y-intercept is changing, you're moving it up. If you're subtracting a number at the end and your y-intercept changes, it moves it down. The horizontal translations are moving it with the relation to x, so in the middle of the problem. Notice when I simplify this one, x minus 3 plus 4 still gets me to x plus 1, but this is moving our function to the right. So if I take my original y-intercept and I move it 1, 2, 3 to the right, this green dot is no longer my y-intercept, but that new y-intercept point is down 3 spaces. So my graph shifted 3 to the right, but my y-intercept moved down. That is why we have the subtracting when we move to the right, because it actually shifts the graph down. On the flip side of that, when I am moving to the left, I am actually adding on to the values. So I still get that g of x is x plus 7, but I am moving to the left now because I am adding in the middle of the equation. So I go 1, 2, 3 to the left, and notice once again, my dot is still over here 3 points to the left, but that y-intercept is now up 7 spaces. So when you're looking at translations, you're looking for, is it added at the end or in the middle to decide vertical or horizontal, and then we have to decide up or down. So now to try some actual example problems, you're always going to be given your original function. Again, it's always going to be f of x. So in this case, I have f of x is equal to 5x plus 3. This first transformation that I have is 5x plus 1. We don't have anything being added or subtracted to the x, so we know that it's vertical because there's nothing here in the middle by x. So that means I have to look at my original and say, okay, how did I get from 3 to 1? In this case, that would mean I would subtract 2 on the end, which means my translation would be down 2 units. Units is the measurement of distance on a graph, so we're going to say we are down 2 units. When I move to my next one, I am looking at f of x is equal to 5, or in parentheses, x minus 7 plus 3. So now my movement is in parentheses, so directly attached to x, so that tells me I'm moving horizontally. And because it's the subtracting, that means I am going right 7 units. You can do both movements within one problem. So if we look at this last example, a of x is equal to 5, and then in parentheses, x plus 2 plus 9, we have a value attached to x, and our final number is also changed. So this number attached to x is our horizontal movement. Because it is a positive or plus x, we are moving left 2 units. And then I need to look at the final number, which is 9, and say, how did I get from 3 to 9? And I did that by going up 6 units. So when we're looking at our translations, we're looking for, did it happen at the end of the problem, or is it in the middle of the problem next to x? And then looking how far we actually moved. Go ahead and try this one on your own. In this case, we've got the double movement again, the -5 moving us 5 units right, and then going from 4 to 1 means we're moving 3 units down. So this is our translations where we slide around the graph without changing the slope. Next, we're going to look at the dilations. Once again, there's the vertical dilations, and then we'll look at horizontal in the moment. When you are doing vertical dilations, this is multiplying the full problem, so both the slope and the y-intercept, by a particular value. So in this example, once again, we're starting with f of x equals x minus 4. I've changed it from plus 4 to minus 4 for this one. And we are looking at our 2 different types. So it can be a vertical stretch or it can be a vertical compression. It is a vertical stretch if the number you are multiplying by is bigger than 1. So a vertical stretch is if you are multiplying by a number bigger than 1. If you are multiplying by a number between 0 and 1, it's going to be a compression. So what does that look like? We have our first one, which was our stretch, and that would, when I multiplied by 2, give me the equation of 2x minus 8. So this red line is our stretch. Notice that the vertical stretch makes it steeper than the original line. When I am looking at the compression then, that's this purple line down here, and that's going to be when I multiplied by a half, so half x minus 2. Notice my vertical compression is flatter than the original blue line. So when I'm doing a vertical stretch, I'm making it steeper. When I'm doing a vertical compression, I am making it flatter. And again, that's multiplying both the slope and the y-intercept by your value. With a horizontal compression, you are only multiplying the slope. So your y-intercept stays the same in these problems. The horizontal values have the opposite of the vertical. So when I am looking at a stretch horizontally, that's between 0 and 1. And then my horizontal compression is going to be when it's bigger than 1 for the number that I am multiplying by. So let me explain why that happens. When you are looking at the original function, which in this graph is the blue line, our blue line originally takes up, I'm actually going to make those bigger so that they are easier to see. So our original blue line takes up this much horizontal space on the graph. So that is how far we are looking at horizontally side to side. When I did my stretch, so when I multiplied by my 2/5, I ended up with 2/5 x minus 4. So what that did was it took my original space on the graph and it stretched it out horizontally. It made the graph wider. So this red line takes up more horizontal space. It got wider compared to the blue line. If I reset this and now I look at my purple line, which is when I multiplied by 5, so a number bigger than 1, that is our horizontal compression. The area taken up by this purple line going from side to side is smaller, more compressed than the original blue line. So when you are looking at the vertical ones, we are looking for steeper being the stretch and flatter being the compression. When you are looking at the horizontal ones, you are looking at wider being the stretch and narrower being your compression. So what does that look like when we actually have our examples? Starting with f of x is equal to negative 4x plus 7. In this first example, I've got g of x is equal to negative 36x plus 63. Right away, I notice that both of my values have been multiplied, so I know this is going to be a vertical change. Then I have to look, how did I get from negative 4 to 36 and 7 to 63? That occurs when you multiply by 9 because it is a number bigger than 1 and we are looking at a vertical change. That is going to be a vertical stretch. So we've taken it and we have multiplied by a number bigger than 1 to both values, so it is a vertical stretch. When we come down here to the second problem, I've got h of x is equal to negative 2x plus 7. So right away I notice I only multiplied one of my values. So I've got a horizontal dilation going on this time. And I'm going to go ahead and spell horizontal correctly for you guys. So horizontal dilation going on. And now again, I need to look, how did I get from negative 4 to negative 2? That occurs by multiplying by 1/2. So since I have a value below 1 but bigger than 0, for my horizontal values, that is the stretch. That is what's going to make it wider. Go ahead and try this one on your own. So when you do this one, once again, you multiplied both values. You multiplied them both by a 3, so that is going to be a vertical stretch. The last piece, the last possible transformation we have is a reflection. This is the easiest one to identify and solve. This is what occurs when you multiply the slope by negative 1. Once again, your y-intercept stays the same. So I go from x minus 4 to negative x minus 4. So what does that look like on the graph? It basically flips your line over the y-axis. So it used to be going left to right going up. Now it's left to right going down. So when we flip, it is changing which side is going up and which side is going down. When you're applying reflections to problems, once again, you are just multiplying the slope by a negative 1. So in this case, my new function would be a positive 5x minus 3. Go ahead and try this one on your own. When you multiply, you get that g of x is equal to negative 2/3 x minus 9. The last piece we have here is putting it all together, being able to actually write the new equations as you are told how to move them. So in this case, we have f of x, once again, that's always going to stand for our original, is equal to 5/2 x minus 1. The function is transformed by moving up 3 units, then right 4 units, then reflecting, then a vertical dilation. So it's putting all of these different pieces together to ask us to find a new equation. So the first thing it asks is for a movement of up 3 units. So I'm just going to go ahead and write my original function. So f of x is equal to 5/2 x minus 1. That original movement is up 3 units. So all I need to do is add 3 onto the end. When I do that, I can simplify negative 1 plus 3. And after my first movement, my function is now at 5/2 x plus 2. Negative 1 plus 3 is 2. So that is my first movement. My next movement is to go right 4 units. Remember, the left and right movements apply in the middle of the function to x. So we need to put that in parentheses. So I'm going to have 5/2 x. We're moving right, so that's going to be minus 4. And then we still have our plus 2 at the end. Now that we have a horizontal movement, we're going to have to use a distributive property. So I do 5/2 times x, which is 5/2 x, and then 5/2 times 4, which is going to give you negative 10, and I still have that plus 2 on the end. I can simplify that down. So after moving right 4 units, my equation is now 5/2 x minus 8. My next movement is going to be the reflection. So I'm going to take this and multiply my slope by a negative 1. So I've got negative 5/2 x minus 8 because I multiplied my slope by a negative 1. The last piece is a vertical dilation. So vertical meaning we multiply both values by 4. So I take both of my values, the slope and the y-intercept, and I multiply by 4, which gives me my final answer, g of x, saying that it's our new transformed function, is equal to negative 10x minus 32. So after my 4 different movements, which you can see by the color coordination here, I end up with a final equation of negative 10x minus 32. Go ahead and write this new function on your own. So we've got down 10 units first, so I'm going to subtract 10 off the end, which gets me to negative 7x minus 4. And then the horizontal dilation means I am only multiplying my slope. So I have g of x is equal to negative 21x minus 4. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.